Hi, hello. Okay, so I'm going to be going through the solutions for question. Is my mic working? Yeah, it is. Okay. So, solutions for question 5 on lab sheet 2B. So that's question 5 from the lab on Friday of the second week of this course. Wow, we're in week 2. Cool. So, right off the bat, before reading anything, we see that this question is hard. And as a second year PhD student, I agree. It's pretty tricky stuff, especially considering we just learned about DFAs. Uh, and I hope y'all have watched the other question solutions because I do believe that the TAs have given some intuition of their own on DFA construction. I will also be doing so for this, and I think the more intuition you have, the better. That and go to in-person lab as much as you can and ask questions. Anyways, so let's read the question. It wants us to construct a DFA that accepts the following language, and the language in this case is all strings W such that f sub this guy that I'm not going to try to read, mod 10 is equal to 4. And then they define this guy to be the number of times we see the substring 1, 0 in the word. And then they say f of n is the Fibonacci number. So right off the bat, this is pretty funky, right? Because we're talking about Fibonacci numbers, but the index of the Fibonacci number is defined by the number of times we see a substring, and then we want the mod, like we take the mod of that Fibonacci number. So it's a lot of stuff. So if you are like me and like you're doing this in the morning, and it doesn't make sense, don't worry, it's fine. They also give us the handy definition of Fibonacci number in case we forgot, although please don't forget about Fibonacci numbers. They're cool, and we should like them. Now, some people's first instinct would probably be to do what we did on Wednesday, which is, just start drawing states. I'm gonna say right now, this DFA is gonna have too many states to draw, unless like you want to spend your time drawing over 100 states. And then you might be wondering, okay, well, how do you know that there are over 100 just by reading this? Well, when I think about DFAs, right, and I've seen them for a while. DFAs are nothing. They're like Python programs in some sense. They're not as powerful as Python programs because I can't go backwards, right? And Python programs, like, I don't have to read an input all the way, like from left to right all the way through. But the reason I talk about Python programs and like we talk about, code when we talk about DFAs is because really like they're pretty similar. And by that I mean when we look at like the state of a program, that state has some information stored, right? So that state has some, I don't know why I repeated that, but there's some information stored at each step of your program. And then the transition is when another bit of information you are getting, okay? So if I take the transition that's labeled 0, that means I've seen a 0. So this is another bit of information that I'm getting, okay? And so even though it seems super simple because we're just talking about states and transitions, I can have my states encode all possible, inputs and like quite literally states of the program, which means even though I don't have the ability to store information, I can implicitly store information in each state, right? And we saw this in Andrew's lecture on, I believe it was Thursday, where I think he had something that was like, you want a language that is, I think, actually, I'm not going to go into that, but look at the example from Thursday's lecture where he had like 6 states and then they were wired up a certain way, but he had like Q00, Q01, and then these were all some kinds of Qs. And this 00 actually meant something, right? And I believe it was that when you're in this state, the counter or the number or whatever the string actually encoded was 0 mod 2 and 0 mod 3, and I believe Q01 was 0 mod 2, 1 mod 3. And so we're going to do something very similar here. And so when we think about what we want each state to encode, we should think about what is the bare minimum information that I need to know along with along with the new character I'm reading. But what is that bare minimum piece of information? And whatever that is, that's going to be the thing that you encode in your states. Okay? And so if we look at the question, we want to get to cases where we have f sub like some quantity, right? Is equal to 4 mod 10. That's what we want. And so and then this quantity is how many times we see the substring 0, 1. So right off the bat, if I know one piece of information I'm getting is the character I'm about to read, it's probably important for me to know what character I've just seen, right? Meaning, if I just saw this is actually 1, 0, my bad. Meaning, is it 1, 0? Yeah. Meaning if I just saw a 1, and I remember that I've seen a 1, and I'm reading a 0, then I know, hey, I've seen another substring 1, 0, and that's going to update this Fibonacci quantity, right? So right off the bat, I should probably let me make a list of things I want my state to represent, list of things I need, okay? So right off the bat would be character I just saw, right? And that's just intuitively what we need. And how many possible characters can I just have seen? Well, the alphabet is 0, 1, so that's what that is. Great. Now we think about what else do we need to determine this accepting quantity, right? Well, I need to know what the value of the Fibonacci of that, of it is. Because look, this quantity is only ever increasing, right? Like I'm only ever increasing the number of substrings 1, 0 I need, which means I'm like going farther down the line in the Fibonacci numbers. So it's probably important for me to store the Fibonacci, like the state I was in last, because that's how I get, actually, okay, what I said was true. And the others, I said this was only ever increasing. Also note, it's only ever increasing by 1, right? This is important. We're only at, so we'll never like miss a Fibonacci number, which I don't think is obvious from the get-go. But because we're only stepping from 1, you know that anytime I get to a new Fibonacci number that's like Fibonacci of this thing that they're asking for, that must have been, by the definition of Fibonacci numbers that they give us, that must have been something like this, right? Or Fibonacci of -2, and we add them together, right? And so it's probably important that I store what those two values are, right? Because then when I read a new character, if that character leads me to read a 1, 0, then whatever the current Fibonacci number I'm at is, like, we move to the next one, which means I should store the current state Fibonacci number and the one I've just seen in order for me to get the next one, because that's the only way I'm able to compute the next one, right? And so I know I've sort of explained that a bit kind of confusingly, but let me write it down first. So if I've seen the number, if let k be the number of times I've seen 1, 0 in W, right? So I want to store the current FK, right? Because that's I'm in the I'm also going to store FK plus 1, right? Again, where K is the number of times we've seen the substring 0, 1. Now, you may ask, why am I not storing FK and FK minus 1? Well, we could, but why would you, right? Because we know the next guy is going to be this. Also, the reason we don't, you can't actually. The reason we don't is because the way Fibonacci numbers are defined is we're given the two base cases, which is f of n is equal to 0, 1, and then the recursive definition here. So if I did fk and fk minus 1, and k starts out being 0, then I can't do fk and fk minus 1. I have to do fk and fk plus 1, right? And so intuitively we can think about this as being the actual, like where we actually are, and this is like next up, right? And so when I get to next up, meaning when I've increased this k, meaning I've seen a 1, 0, then we store fk plus 1 and then fk plus 2, right? And then we keep shifting like that. Okay, cool. So, now I have this list of 3 things that I need. And we should also talk about what sets these entail. Now, if we weren't talking about mods, we'd be kind of screwed because the Fibonacci numbers are not bounded, right? But we're asking for the Fibonacci numbers mod 10. Yeah, I miswrote this. We're asking for the Fibonacci numbers mod 10, okay? So because we're asking for these mod 10, we know that the only values of fk or fk plus 1 mod 10 are 0 all the way up to 9, right? And that's the same for this one, 0 all the way up to 9. Great. So that means each of our states encodes these 3 things, okay? And by product construction, which again we learned on Thursday, I can denote my states as follows, okay? I'm going to call it, what variables do I want to use? I'm going to say C, F, and B, okay? Where C is the current FK mod 10, right? F is the future, meaning just the next one, future FK mod 10, where this is just FK plus 1, right? Or the future FK is FK plus 1, and then B is the bit we just saw, right? Okay, and so if my set Q is going to be states labeled like this, where C and F both come from 0 all the way to 9, and B comes from the set 0, 1, how many states are there? Well, there are 10 elements in these, so that's 10 times 10 times 2, and that's 200, right? And so that answers our first question, well, how do you know there are so many states? Well, I know because, like, intuitively I knew that I had to encode some Fibonacci numbers and mod 10, and I knew that I needed 2 because they're Fibonacci numbers, and the only way I get to the next one is by knowing at least 2. And so from there, I could guess. But again, I'm a PhD student, and even I got stuck. I'm editing out this long string of silence that was there a couple minutes ago, and I got myself confused. Anyways, okay, great. So now we have one part of our DFA. We know that sigma is 0, 1. That's great. And the other elements of the DFA tuple are delta, S, and A. So that's all we need to do now, because we got sigma, we got Q. Let's talk about S, the starting state. So the starting state is where I go before I've read any characters, right? Which means the number of substrings of 1, 0 that I've seen. There are 0 substrings of 1, 0. Which means F0, that's 0, and then mod 10 is also 0. So that's what my current Fibonacci place is. Then we know the second place has to be F1 mod 10. So I'm going to call this C0. This is F0, and then this is B0. Yeah, so I know that the second place is 1, and then the question is, well, what do I put in the bit spot, right? Well, we want to make sure that, like, whatever we put here never counts towards a substring 1, 0, right? Because that would be bad. That would be counting something that isn't actually there. And so the way to guarantee that is by putting a 0 down, because if I had a 0 and if I just seen a 0, there's no way whatever character I read next is going to give me a 1, 0, right? Which is another really nifty trick. Think about, like, at least for start states, right? Think about how I prevent extra counting of certain conditions of happening, and the way we do that here is by putting a 0 down. Okay, great. So that's 0. So that's the start state. There are no other start states, right? Because I know the first two have to be 0, 1, and if I made the last bit 1, then I could accidentally count a 0. So there are no other start states. I don't know why I put this in set when it's not really a set. I mean, if it was an NFA, it could be, but I'm just gonna say S is that. Okay, great. Now we should talk about delta. Okay, and you might be thinking, well, there are so many states. Delta, the way delta is going to be defined, is a mess. And to that I say, no, not really, because we can just talk about, or in the solutions they talk about, they call it C and F, or Q and R, and I call it C and F. But we can talk about those quantities generally, right? Because they're just numbers, honestly. So and then I'm gonna call that new bit. So really, we're gonna define this for all possible values, okay? And all possible values really conditions over the bits we've seen, okay? By that I mean we only need to figure out what happens when I have CF, I've just seen a 0, or I've just seen a 0 and I see another 0, right? And then we do the same for CF, I've just seen a 0 and I've now seen a 1. CF for delta of CF, I've just seen a 1 and I now see a 0. And then CF, I've just seen a 1 and I've now seen another 1, okay? And we just have to define those. Now, the only really interesting case is when I've actually, like, have seen a 1, then see a 0. Why is that? Well, that's the thing that actually increments my K counter, meaning increments the number of times I've seen the substring 1, 0, because that's the only time I see a 1, 0, right? Right here. Okay? For all the other cases, my computer just, yeah. For all the other cases, because I don't see the substring 1, 0, I don't change that counter. And if I don't change that counter, the value of the Fibonacci number doesn't move up, right? Like, I don't get to the next Fibonacci number mod 10. And so for all of these, I stay at CF, right? But I do update what I've just seen. So in this case, I just saw a 0. In this case, I just saw a 1. And in this case, I also just saw 1, right? But in this case, I don't. In this case, I've seen a 1, 0, okay? Which means the thing that goes here is a 0, because I've just seen a 0. And I've seen another instance of the substring 1, 0, which means I move to the next Fibonacci state, the future Fibonacci state mod 10. And so now what's left to do is just compute what the next future value is, right? And the way I do that is by saying, well, if C was the kth fk mod 10 and f was fk plus 1 mod 10, and this needs to be fk plus 2 mod 10, then I just do C plus f mod 10, right? And you might be wondering, well, oh, can I, but these are just mod values, right? But you should remember from handy dandy 173 that modular arithmetic holds over addition. So just because I take the mod in the beginning won't affect the mod at the end. And if you don't know what I mean by that, please come to office hours and ask if you're confused about the mod stuff. Great, and that's my transition function. Wasn't too bad, also pretty intuitive once we understand exactly what the states encode. Okay, now the last thing to talk about is A, and where A is the set of accept states, right? And so what's our accepting condition? Our accepting condition is if f sub whatever, f sub k, where k, again, k is the number of times we've actually seen the string 1, 0. If fk mod 10 is equal to 4, then I want to accept, okay? And how is that represented in my states? Well, if my state is labeled with a 4 in the current section, right, I don't really care what the next Fibonacci number is. I just care that currently I'm at a Fibonacci number that's 4 mod 10. And I also don't care what this last bit is, right? But really, the accepting condition only gets represented in the first element of our tuple here, which means A can be defined as the set of tuples for our, why did I call this R? For FB, right? Where F can be anything, and B is either 0 or 1, okay? Great. And so that's the last element of our checklist. We talked about delta, we talked about S, we talked about A. Great. We didn't have to draw it, right? And so for those of you who ask in discussion sections like, hey, when would I use the formal definition? In scenarios like this where drawing it would be an absolute pain in the butt, right? And so that's it for the construction. There is a part of the solutions that I think I should just briefly explain in case there are any questions about it, that says the Fibonacci numbers mod 10 define a repeating sequence with period 60. So this language can be accepted by a DFA with only 120 states, okay? And you might be wondering, well, what? So what they're trying to explain is, hey, we're not just looking at the Fibonacci numbers, we're looking at the Fibonacci numbers mod 10, and I don't know how much stuff they talk about in 173, but sometimes when we look at the mods of certain numbers, they don't actually hit all possible values 0 through 9, right? Sometimes they only hit certain values. I think an example is like if I take the squares of a number, so if I take s square mod 4, I think, someone can triple check. This is not important, by the way, but just in case you're curious, I think if you take the squares mod 4, you won't get any value that's equal to 3. And I also believe you won't get any value that's equal to 2, right? And that makes sense because if I have some number s and I look at it mod 4, that value can be 0, 1, 2, 3, mod 4. And so when I square any of these, I get 0. 1 squared is 1 mod 4. 2 squared is 4. And 4 is simply 0 mod 4. And 3 squared is 9. And 9 is again 1 mod 4, right? And so basically I've observed that, okay, well, take any square number and take it mod 4, I'll never get a 2 or a 3, which means I can eliminate those values. And in a similar kind of like notion, same thing happens with Fibonacci numbers. You don't need to know that, right? This is just a fun fact that like an expert on Fibonacci numbers or a Fibonacci enthusiast would know. And if you were trying to optimize DFA design, which I don't think we're going to get too much into, that would be the case. But they say making this observation, you'll only need a DFA with 160 states. That's because the only thing you'd need to encode is the current state you're in, and then the new bit you've seen. Okay, and then you might be asking, well, why don't I have to include the previous state? Well, the observation they make is the Fibonacci numbers define a repeating sequence with period 60, which means if I have F0, F1 all the way up to F59, this defines some number. So say it's like 9, 3. It's definitely not 9 and 3, but like I'm just making it up. All the way up to 7, and say there's like 9, 6, 5, whatever. It's some sequence, okay? And then after this 7, it loops back to 9, 3, right? And so if I know that this sequence just loops continuously, I don't have to actually calculate the next Fibonacci number, right? Because like I just make a state for each of these guys with 0 and 1, and then I know that the next one will be the next guy in the sequence, okay? Which means there are 60 possible values for the current state, but now this 60 denotes what place each of these guys are in the sequence, and then there are only 2 values for this bit, and that's 120, okay? But 120, 200, kind of the same thing, in my opinion. Not really, but yeah, so I hope this was helpful. Please ask questions on Piazza. Please come to discussion sections. Please come to office hours early in the week if you have conceptual questions, because getting your conceptual questions answered will really help you with the homework. What else is there? Stay safe, stay healthy. Don't, for the love of God, party. Be sure to like, comment, and smash that subscribe button. Click the bell. I'm having way too much fun with this outro thing. Anyways, all right, bye guys.